What's up, everybody? Here are the solutions for worksheet number 7, and problem 1 asks us to analyze this function over here, and for part A we're asked to find the critical points. In order to find the critical points, we must first take the derivative of our function, and the critical points are going to be the points where either the derivative is undefined or where the derivative is equal to 0. So let's see what we get. First I have to differentiate this term here, so I bring down the 1/3, I get x minus 1 to the negative 2/3 and minus 1/12. I set that equal to 0, and before I do any kind of algebraic manipulation, notice that this exponent is negative, which means x minus 1 is in the denominator, so automatically f prime is undefined at x equals 1. The solution of this equals 0. Okay, so now let's move the 1/12 to the other side. I end up with, and I'll multiply by 3, so I end up with x minus 1 to the negative 2/3 equals 1/4. Once I multiply by 3, I get rid of that constant. And since I don't want my exponent to be negative, let's flip everything. So x minus 1 to the 2/3 equals 4. Now what I can do is I can take a square root to get rid of the 2 in the exponent, and then cube everything. So that means x minus 1 is going to be, okay, first, since I'm taking the square root, that is going to give me a plus or minus 2, and then I cube that, so this is plus or minus 8. Okay, so we actually end up getting two solutions here. We don't want to miss that. And then I just move the 1 to the other side, so I get either x is equal to, if 8 is positive, I get 9, and the other solution is x is equal to 8 is negative, I add 1, minus 7. So here are the three critical points: 1, 9, and negative 7. And for part B, now we're asked to find the absolute maximum and absolute minimum of our function. However, we're specified this interval here, so that means we're only going to be looking at the critical points x equals 1 and x equals 9, because those are the only two x values that fall within the interval 0 to 28. Right? We have to omit the x equals 7 point. Alright, now here's how we're going to do this. First, since we're given a closed interval, let's write down our x values. So the smallest x value is 0, the end point of the interval. Then comes 1, then comes 9, then comes 28. And let's plug in values for f of x at each of these points. When I plug in x equals 0, I get, well, f of x was negative 1 to the 2/3 minus that, so this term is 0. This term is going to be negative 1 to the 1/3, which is negative 1. How about if I plug in x equals 1? That's going to be 0. I get negative 1/12. How about for 9 now? Okay, I plug in 9. 9 minus 1 is 8. Cube root of that is 2 minus 9/12, which is the same as 3/4. So let's see, what does that come out to be? This is 8 minus 3/4, so that's 5/4. And lastly, we're going to plug in 28. 28 minus 1 is going to be 27. Cube root of that is 3. Let's write it down here. And then I subtract 28/12, which is 2, and that gives me 1. Okay, and now we have this list of values. We're asked to find the absolute max and min, so we're going to have to take the smallest possible value and the largest. Now the smallest value we see is going to be this -1 here, so that is the min of our function, the absolute min on this interval at least. And the most positive, well, 5/4 is greater than 1, is 1 point something, and so we're going to be picking this one for the. Note, when we're asked
to find an absolute max or min of the function, we are actually interested in the values of the function, not just the x coordinates here, right? So these are the ones that you want to specify. All right, let's take a look at the next problem. For this one, we have something similar, right? We're given a function, and first we're asked to find all the critical points. So we're going to do the same thing, right? We're going to take the derivative g prime, and we're going to see where it's undefined and where it has zeros. Those are going to add up to being all of our critical points. Okay, the derivative here we have to use a product rule. So it's the derivative of the first, which is 1 times e to the minus 2x squared, plus the first times the derivative of the second, which is e to the minus 2x squared times -4x. And we set that equal to 0. Notice that the derivative is defined everywhere. We don't have anything like a 0 in the denominator or anything like that, so it's valid for all real x, which means the only critical points we can have is once we set this equal to 0. Now, since the exponential function, its graph looks either like this if the exponent is positive, or like that if the exponent is negative, it's never going to cross the x-axis. It's always going to be above the x-axis, and this is true for every exponential, no matter what the base is. So that means this is never 0. In particular, we can 1 plus -4x squared, right, by combining this x with that x, equals 0. So that means that x squared is going to be 1/4, or x is equal to plus and minus a half. So we get 2 critical points here. Okay, for part B of this problem, just like in the previous problem, we're asked to find the absolute min and max. So, but we're also given the interval here. So that means we have to omit the critical point -1/2 because that's outside this interval. And we're only interested in the endpoints of the interval, so 0 and 1, as well as the x equals 1/2, the critical point of our function. So let's take these numbers and plug them into G. And see what we get, right? G of 0 automatically is 0 because we're multiplying by this x, so that's 0 here. G of 1, that's 1 times e to the minus 2, so it's just e to the minus 2. And G of 1/2 now, let's see, what do we get? Again, 1/2 e to the minus 2 times a half square, so 2 times a fourth. So this is 1/2 square root of e, I believe. That looks right because this exponent is 1/2, but it's negative, so we have a square root e in the bottom, and then I get a 1/2 in front. So this is 1/2 square root of e. Now, obviously, since the exponential is never 0, this is going to be my min. Automatically, the 0 is going to be my min. However,
we're going to have to figure out which one of these is our maximum. So let's take a look on how we do that. We have to compare the two. So I have to compare 1 over 2 root e with 1 over e squared. This is the same as comparing 2 root e with e squared, which is e times e. Now, e is approximately 2.71 as a decimal, so automatically 2 is going to be smaller than e. 2 times root e is smaller than e times root e, and because e is a number greater than 1, that's smaller than e times e, right? By comparing these two guys, the root is going to be smaller than the number itself. So what this tells us is that in this comparison, the 2 root e is the smaller of the two, and by taking the reciprocals, 1 over 2 root e is the larger number here, so that is going to be my maximum. Alright, let's move on to the next problem. And here we have the problem that showed up on our quiz, and we started out with the last question that was on the quiz, which is to find the time t in terms of x. So I know that t, total time, is going to depend on the time spent on the road, the time spent in the woods, plus the time spent on the road. And I know time is distance divided by velocity, just by doing a unit analysis. So the time spent in the woods is the distance spent in the woods, which is square root of x squared plus 9, which is the 3 squared here in this right triangle, divided by 10, which is the velocity of the biker through the woods, plus now the distance on the road, which is 6 minus x, divided by the velocity there, which is 20. And what I'll do here, just to make my life easier in the next step of the problem, is I'll factor out a 1/10, and I will write this as square root x squared plus 9 plus 6 over 2 is 3 minus x over 2. So that's the total time in terms of x. Now for part B, we're asked what are the possible values of x for which you should minimize this function, and that means we have to look at our physical problem and see for what values of x this question even makes sense, right? What's the smallest x could be and what's the largest it can be. So it's fairly obvious that to get the best result here, you don't want x to be negative, because you would be traveling some path, down this way, and that's just going to take way longer time. So x should be definitely greater than or equal to 0. And you also don't want to have x larger than 6, because you'll be traveling way far out here and then coming back to return to the restaurant. So x should not be larger than 6. And in interval notation, this is 0, 6, and we're able to close the brackets because notice t is defined at those points, so we can actually attain these values of x. This is a closed interval. So that's part B. And now let's take a look at part C, that is asking us to actually find the value of x that minimizes time. So again, I'm gonna use what I had on the quiz earlier. This was the formula, so let's rewrite it. T is 1 over 10 square root x squared plus 9 plus 3 minus x over 2. And I want to find the derivative of this in terms of x so that we can find the minimum of the function. So t prime of x now, 1 over 10 stays, and I just work with the inside now. So this is 2x over 2 square root x squared plus 9. The 3 drops because that's a constant with derivative 0, minus a half. And I have to set this equal to 0. Also, I have to ask the question for what values of x is this undefined, and this is defined for all real numbers x. And the reason for that is because in this denominator, this square root part is always positive. We have the plus 9 over there. If this was a minus 9, the situation would be a little bit different. Okay, so let's see. We have this derivative. We have set it equal to 0. And to find the critical points, I know I have to solve for x. First thing I'll do is I can get rid of the 1/10. I can cancel the 2's here. So what I'm looking at is x over square root x squared plus 9 equals, move the half to the other side, just like so. Then I'm going to cross multiply. So I have 2x equals square root of x squared plus 9. And let's square everything. So let's square both sides. I end up with 4x squared equals x squared plus 9, which now allows me to combine the square terms together. So I have 3x squared minus 9 equals, actually I'll leave the 9 where it was, and you'll see why in a second. I have 3x squared equals 9, divide by 3, so x squared is equal to 3, which means x is plus or minus 3. However, since we are talking about time here, and remember from the previous part, x was only in the interval 0 to 6, we're only going to be interested in the positive solution of this. So we only want x equals plus 3. That's the one that we want. Now we want to minimize t at that value. So, or at least we want to now argue that this is a minimum. And there's a couple of ways to do that. One, we could make a table and we can just plug in 0, 3, and 6, and we'll find that this is going to be indeed the lowest value that t takes. Or we could just take the second derivative and look at the concavity of the function, right? You'll have to take my word for it. I won't do it now, but you'll have to take my word for it that if you plug in 0, 3, and 6 into t of x, that we do indeed get this to be the minimum. So let's move on to the next problem now. We have a function, f of x is x ln x squared, and we're asked to find the derivative. Before I even do that, let me rewrite this a little bit so that it's a little easier to work with. So I'll bring the exponent in front of the log. So this is 2x ln x, just because it makes my chain rule a little bit easier down the road. So if I want to find the derivative of this now, f prime of x is going to be, derivative of the first is 2 ln x plus 2x, and the derivative of log is 1 over x. So this is the same as 2 ln x plus 2. Now we want to verify that the function satisfies the hypotheses for the mean value theorem, and the mean value theorem basically states that if the function is continuous on a closed interval, which we're given here, 1 to e, and differentiable in the open interval 1 to e, then it satisfies the conditions, right? So so let's see, is our function continuous there? Yes, because the log is continuous from 0 to infinity. X squared is continuous everywhere, so that's a composition of continuous functions, and that's also a, multiplying by x doesn't change continuity. So f of x is continuous on the closed interval 1 comma e, and the derivative, which is 2 ln x, is defined for all real greater than 0, real x greater than 0. In particular, is defined on the open interval 1 comma e. So that means that there exists a constant inside this interval such that if I evaluate the derivative of that constant, it's going to be equal to the average rate of change of my function over that interval. So f of e minus f of 1 over e minus 1. And just to draw you a picture of what that's going to look like, let me do that up here. Basically what this is saying is that if I have some function that looks like this, differentiable everywhere from a to b, then whatever the average rate of change is here, which is the slope of the secant line here, that's going to be attained by some tangent line over there. Okay, and this is the c that we're looking for. Okay, so let's see, how do we find this value of c? First I need to figure out what the average rate of change is going to be, so I have to compute f of e minus f of 1 over e minus 1. Now f of e is 2e ln e, so 2 times e, minus f of 1, ln of 1 is 0, so that's just 0, over e minus 1. So this is 2e over e minus 1, and I want to find some number for which the derivative attains this value, right? So this is the average rate of change, and I want to set this equal to my derivative, which I found here, and then solve. So I'm going to set this equal to 2 ln x plus 2. Excellent. So now in this equation here, what I'm going to do is first I'll divide by 2. I don't like having those there. So I have e over e minus 1 equals ln x plus 1. And I guess the next step would be to move the e to the minus 1 to the other side. And so let's see what we get. So I have e is equal to ln x plus 1 times e minus 1. And let's multiply it out. So this is e ln x minus ln x plus e minus 1. So what I have now is the following. I have e equal to this part right here. Let's go ahead and cancel these e's. I'll move the 1 to the other side. So I have 1 is equal to factor out the ln x times e minus 1 and let's see, what do I want to do now? Let's go ahead and move the e here in the denominator, so I have 1 over e minus 1 equals ln x, and since I'm trying to solve for x, I'm just going to go ahead and exponentiate both sides, so x is going to be e to the power 1 over e minus 1, just like so. So it's kind of a messy answer here. It's not the nicest value of x, and I'm realizing this now that I could have just done that here. I could have just said, okay, ln x is e over e minus 1 minus 1 by moving this one to the other side, and I could have made this a lot quicker. So this is the same as e minus 1 over e minus 1 by combining these. I'm writing this one as the fraction e minus 1 over e minus 1. So this is the same as 1 over e minus 1, which is what I had here. So I could have skipped this multiplication step. But this is the answer right here. And that's the number c that if I plug in the derivative, the slope of the instantaneous rate of change here at this x value is going to be equal to the average rate of change over the interval 1 comma e. And that's it. That's the end of the worksheet. Till next time.